It's really my great honor to have this opportunity to share our thoughts on how data management software could benefit from emerging storage hardware with built-in transparent compression. As the CMOS technology scaling is reaching to its limit, the computing infrastructure is transitioning from the traditional CPU-only homogeneous computing towards domain-specific heterogeneous computing. Here, the certain computation tasks migrate from CPU to other computing engines, such as standalone PCIe accelerators, smart network card, and the computational storage drives. Altogether, they complement with CPU to form a truly heterogeneous computing infrastructure. The basic concept behind computational storage is very simple. We just make each storage drive be capable of performing certain heavy-duty computation on the I/O data path. This will form a highly distributed heterogeneous computing infrastructure that can maximize the computation parallelism with minimal extra data movement and latency overhead. In the heterogeneous computing landscape, regarding the commercialization of computational storage, data path transparent compression apparently is the first low-hanging fruit to pick. Its basic idea is very simple. Compression is done in hardware on the I/O path, completely transparent to the OS and the user applications. Our current product uses a single FPGA to handle both flash control and per 4K byte Z-lib compression. We implement flash translation layer in the kernel space driver that exposes the drive as a standard block device to the Linux block layer. This cartoon further illustrates its difference from current practice. On the left-hand side is a current practice, where we use either CPU or accelerator to handle both data compression and deploy normal SSD. The right-hand side shows the computational storage drive with data path transparent compression. Here, a single FPGA combines the functionality of a flash controller with a hardware compression and decompression engine, and enables a convenient plug-and-play solution for end users. The drive frees up host CPU cycles, minimizes the data movement, and enables a compression throughput to scale with the storage capacity. This slide shows the basic FIO testing on our drive and on a competing high-end NVMe drive. Both drives are 3.2 terabyte. FIO generates heavy I/O workload across the entire 3.2 terabyte storage space. The three figures here show the random IOPS, where each I/O request is a 4K byte, 8K byte, and a 16K byte. In each figure, the horizontal axis is the read percentage in the I/O workload. As the workload changes from read-only to write-only, the IOPS of the normal NVMe drive significantly drops because of their internal garbage collection overhead. In comparison, in our drive, the built-in transparent compression can on the fly reduce the write data traffic, leading to a much less internal garbage collection activity. As a result, not surprisingly, drive with built-in transparent compression can achieve much higher IOPS as shown in the figures. Beyond the direct benefits in terms of cost and the random IOPS, transparent compression decouples the logical storage space utilization efficiency from the physical storage space utilization efficiency. In particular, as illustrated here, with transparent compression, we no longer have to fill each 4K byte sector with valid user data, and we no longer have to use all the LBAs. So as a result, OS and applications can purposely underutilize the logical storage space in return for performance and benefits. And meanwhile, without sacrificing the true physical storage cost. This opens unique opportunities for system-level innovations. To demonstrate the potential, our position paper presents 3 case studies. Due to the time limit, here I will only go through 2 case studies, and please refer to the paper for more details. The first case study is about Postgre, the second most popular open source relational database. Postgres uses a parameter called a fill factor to control the amount of space reserved in each page for future updates, which further determines a trade-off between the database performance and the storage cost. If we reduce the fill factor to leave more space for future updates in each page, the database performance will improve, especially under the write-intensive workload. But meanwhile, the storage cost will accordingly increase. As a result, Postgre by default sets the fill factor as 100 in order to minimize the storage cost. Interestingly, once Postgres runs on storage drive with transparent compression, the storage overhead caused by the reserved space will largely disappear, since Postgres initializes the reserved space as all zero, and the transparent compression can highly compress the all zero segments. So this naturally enables Postgres more aggressively set the fill factor without sacrificing the physical storage cost. To illustrate this, let the blue and the black dots represent the operating points when using our drive and a normal NVMe drive. With the default fill factor of 100, they have the same performance, and our drive can reduce the physical storage cost by half through the transparent compression. Once we reduce the fill factor to 50, on the normal drive, the storage cost directly doubles and the performance improves. Very clear trade-off between the performance and the storage cost. Under our drive with transparent compression, we can expect the same performance improvement, but meanwhile, the storage cost remains largely unchanged. So we further carried out the Sysbench-TPCC benchmarking. Here, we consider 2 different data sets size, 740 gigabyte and 1.4 terabyte. The results here show that as we reduce the fill factor from 100 to 75, the TPS performance can improve by about 33%. On the normal NVMe drive, the physical storage space jumps from 740 gigabyte to 905 gigabyte, or from 1.4 terabyte to 1.7 terabyte. In comparison, under our drive with transparent compression, we see the same 33% TPS performance improvement. And meanwhile, the physical storage space only slightly increased, like from 178 gigabyte to 189 gigabyte, or from 342 gigabyte to 365 gigabyte. This study clearly shows that by configuring the fill factor parameter, Postgres can very nicely take much better advantage of transparent compression to further improve the TPS performance without compromising the physical storage cost. The second case study is about the key value store. In conventional practice, hash-based key store must use an in-memory hash table to maintain the mapping from the key space to storage space. Thus, such indirect addressing through the intermediate hash table can ensure the compact placement of key pairs on the storage space and hence maximize the storage space utilization. Meanwhile, the memory footprint of a hash table is directly proportional to the number of key pairs. This leads to a very high memory cost for the large-scale hash-based key stores. The high memory cost of a hash-based key store is arguably the main reason why its real-world deployment really pales in comparison with TV stores built upon other more memory-efficient data structures like log structure and merge tree. Leveraging the storage hardware with built-in transparent compression, we propose a table-less hash-based TV store as illustrated here. We directly hash the key space onto the logical storage space without going through the hash table. By avoiding the use of the hash table, it essentially eliminates the memory cost barrier on implementing hash-based TV store. Moreover, by relieving CPU from the managing and the searching the hash table, it consumes less CPU cycles. As discussed above, the indirect addressing through an in-memory hash table can ensure the compact placement of TV pairs on the logical storage space. In contrast, the proposed table-less approach is subject to significant underutilization of the logical storage space. That is, all the pages have big chunk of empty space left unutilized. Once we fill the unoccupied space with highly compressible dummy data like O0, storage hardware with built-in transparent compression can maintain high utilization efficiency of the physical storage space, despite very low logical storage space utilization. Such a table-less hash-based TV store has several appealing properties. First, very simple data structure. It has a very simple code base and can easily achieve high operational parallelism. And apparently, it has a very small memory footprint, and also it's free from frequent background operations like garbage collection and compaction, so which leads to low and consistent CPU usage. We have developed a prototype compared with the RocksDB. It can achieve more than 2 times better throughput performance and more than 2 times better, less CPU utilization. We will open source the design, and we're looking for collaborations to together grow the community. So in conclusion, by decoupling the logical storage space utilization efficiency from the physical storage space utilization efficiency, the emerging storage hardware with built-in transparent compression create unique opportunities to rethink the design of data management software. So it is our hope that our preliminary case studies will contribute to attracting more research interest and activities towards this unexplored territory. This may lead to many more opportunities to innovate future data management software. So this ends my talk. Thank you very much.